So it's my first day here at the boot camp. I'm right back from vacation, so I couldn't join earlier, unfortunately. But it's my pleasure to be here today. So Mirjana asked me a few weeks ago whether I could do a quick presentation about one of my recent papers that I did, which was called 50 Nifty Variations of Two-Transistor Circuits. And I gladly do, yeah, because it was a fun paper, and this should be a fun presentation, yeah, so please don't take it all too seriously. But still, I think it has an underlying theme, and that is that the MOSFET transistor is just incredibly powerful, and circuit design in CMOS is just super cool. Yeah, so I think that's the main takeaway, and we'll get there in a minute. So luckily, I didn't have much time due to my vacation being just in the middle of the preparation time, but I could reuse a talk I gave a bit earlier at an online forum. I hope you haven't seen this one, so otherwise it would be just a rerun. Yeah, so I hope it's new for you. So why am I here? Yeah, so you might have seen this. Actually, in the summer 2021, Solid State Circuits magazine, we published an article. So me and Matthias Eberlein, which was a PhD student of mine at this time, and it was called 50 Nifty Variations of Two-Transistor Circuits. Yeah, you see already from the title, yeah, this is something fun, yeah. And a bit later, yeah, I also published a LinkedIn post, we'll see in a minute, and this was also very, very popular. And I think this triggered the whole thing essentially. So this was the LinkedIn post. Yeah, at some point I just decided, okay, the theme of this paper, which is essentially 50 circuits, useful circuits, made out of just two transistors, yeah, would also make a good poster. And so I spent 1-2 hours, yeah, and just made a poster out of it, put it on our institute's walls, printed out in big, and then it's just okay, I have it, let's post on LinkedIn, yeah. And then, yeah, I did this on a Sunday night, and then, I don't know, I would say it went viral, yeah. So I had tons of reactions to this post. People really liked it, and I was pretty much blown away. So you might have seen this as well. Yeah, I had lots of reactions on this one. So now the question is, why write such an article in the first place? Yeah. So as I already said in the beginning, yeah, it's a fun article, and for me it's also kind of a testament and a celebration of the ingenuity and creativity of circuit designers. Yeah, I find this just cool. Yeah, what people can come up with. And also it shows the versatility of the MOSFET. Yeah, I really like the MOSFET. It's a great transistor, much more powerful than a bipolar transistor, because depending on how you bias it and operate it, yeah, it can work as a switch, and a very nice switch in the voltage and the current domain. This is great. You can use it as a resistor, and not only as a resistor, yeah, you can use it as a variable resistor, a voltage controlled resistor. So another great use. You can use it as a capacitor, pretty non-linear, but you can use this to your advantage. So another great use. You can use it as a diode, essentially. You can use it as a current source, and again, as a controlled current source, yeah, a voltage controlled current source, and as a plain transistor, yeah. So you see, all of these are, I would say, the main ingredient of an analog circuit designer you can build out of the MOSFET. I mean, that's just great, yeah. You can use, of course, a linear resistor, a linear capacitor, which are often used in technologies, but you can get around it, yeah. If you just have a MOSFET, you can do a lot of useful stuff. So this is great. So a couple of years ago, I don't know, a thought appeared, and I was just thinking, okay, since you can do so many things with a transistor, yeah, how many circuits are there with just 2 transistors? Why 2? I mean, a single transistor, I mean, okay, the possibilities are ending, yeah. 2 transistors, who knows? And 3, you'll see in a minute, is just incredibly large. So since a couple of years, yeah, I was just collecting, yeah. Since I'll do anyway a lot of paper reading whenever I stumbled across an interesting 2 transistor circuit, I put it into my archive. And sometime 2021, yeah, I just felt impelled, so okay, let's write the paper. Now I have enough, yeah. And then I had around 25 to 30, and then writing the paper, and then we made again an intensive search, and in the end it was 50. Turns out I was not the only one interested to just see, okay, how many different configurations can you find? So there is one paper already from 2001 where they made an exercise, yeah, just trying to find how many configurations of a MOSFET could you have. And there is another paper here from 2018, and this gives you the numbers. I mean, and this is just staggering, yeah? If you just think about, you take 2 transistors, each of them being a 4-terminal device. How many unique configurations can you find? And turns out, if you calculate the numbers, it's 582 of just 2 transistors. Yeah, I mean, that's a lot. When you do this with 3 transistors, it's already 56,280 possible configurations. I mean, it's just mind-blowing. Yeah, and I think this is also one of the reasons why people still can come up with circuits with just a few transistors, which are unique. I mean, for sure, no one has so far, you know, found all 56,000, or let's say the usefuls of them. So there's still even 2 transistor circuits showing up. And now you could say, okay, 50 circuits with 2 transistors is a lot. True, but if you compare out of these 582, I mean, that's not even 10%. Yeah? So there's still room to explore, yeah, new transistors to find. So I think that's just interesting, yeah, to look at how it's possible. So now you're a circuit designer and I give you 10 transistors. I mean, I don't know what the number is, yeah, but I mean, the possibilities are almost endless. Yeah, just think about it, what you can do with 10 transistors. Okay, so now let's jump into the 50 circuit snippets that we collected. As I said, all of them work. Most are useful, some maybe not so much, but let's dive in. So this configuration, the first one, you know for sure, yeah. I mean, that's the ubiquitous digital inverter, yeah. It consists of an N MOSFET and a P MOSFET, and depending on the input, yeah, you pull it either to ground or to VDD. The output does the inverse, yeah. Just plain old simple inverter. By the way, in my 50 circuits, I did not just double everything up to make an NMOS and a PMOS version. Yeah, so this would be too simple. I didn't do that in my 50. You can take either 2 NMOS or 2 PMOS or an NMOS and a PMOS. That's it. Yeah, making just the inverse circuit. Yeah, I mean, that's too simple. Okay, so that's the inverter. Everyone knows that. Another absolute classic, yeah, is the current mirror. You see now. You have 2 transistors, one connected as diode, the second in a common source configuration. It's a perfect, almost perfect, let's say, replication of the current from the input to the output, and you can scale it. I mean, it's already super cool, yeah, but just defining the geometry of the MOSFET, you can scale the current up and down. I think that's also an all-time classic. Yeah, you use this configuration a lot in IC design. Another all-time classic is the differential pair. So you connect the sources together, you feed it with a current source in a real differential pair, so to speak, or you tie it to ground in a pseudo differential pair. Both are useful. If you connect it to ground, you have, in addition to everything else, kind of a class AB behavior, which can be quite helpful in some cases. So you apply a differential voltage at the gates and you get the differential current out. So used very, very often in mixers, in operational amplifiers. Yeah, I mean, tons of uses for the differential pair. And by the way, you see here the references. So I also tried when doing this paper, find the original reference, which is sometimes tricky. But when interested, you can look up the references and just read what I think is the original paper. Yeah, and another very well-known two-transistor circuit is the transmission gate, consisting of an N MOSFET and a P MOSFET. Yeah, it switches nicely voltage or current depending on bias conditions. So I think I would say, so these 4 circuits are, I would say, very well known. Every circuit designer knows them, and we use them very, very often. Some look very, very similar, yeah, let's say from a circuit configuration, but they are actually differently used. So if we look at this configuration, yeah, that we just had, this is the digital inverter. But now you can do something with the output, yeah. If the output just slams between VDD and ground, yeah, this is a digital operation, but you can keep the output by proper biasing somewhere in the middle so that both MOSFETs operate not in a triode region, but in the saturation region. And then depending on what you do at the output, you have either a voltage amplifier, a low voltage, pretty good voltage amplifier, or you can use it as a transconductance cell. The good thing is with bias current reuse, because the same bias current goes through M1 and M2. So you add up effectively the transconductance of both transistors. And turns out with the CMOS technologies going into the scaling regime, yeah, where the voltages get really low, people are using more and more this simple circuit as a transconductance cell. And it works surprisingly good. So you see the same structure, let's say same connection, same physical structure, but operated completely different. Yeah, here the output is just slamming rail to rail, and here you keep it in the middle, and you have a nice analog circuit. Yeah, so, and I count this as a second circuit. Yeah, I mean, even if it's the same configuration, but used differently, I'd say, okay, that's enough of a reason to say that's a different circuit. In my opinion, it is. And you can play this game differently, yeah? Here I have now 4 examples where we have the same arrangement of transistors, again, same configuration, but an operation of the transistors in a completely different way. So let's go through it, yeah? So everyone knows this configuration. You have 2 transistors in series connection. So that's the pull-down branch of a logic NAND gate, yeah? So if both inputs are logic high, the output is tied to logic 0. Yeah? And to complete the NAND gate, you would do a parallel connection on the PMOS branch, on the pull-up branch. Yeah, so I think that's obvious. Yeah, you apply rail-to-rail inputs, and you get a logic rail-to-rail output. First operation, hard switching of the transistors. This is the same physical arrangement of transistors, but a completely different thing. Now you operate it in an analog way, and that's a cascoded common source stage. So you apply an analog input to the lower transistor, you put the cascode transistor on top, and you have a cascoded common source stage. Completely different operation, right? Same physical arrangement. Again, I count this as a new circuit. Yeah? Then you can swap the inputs. Yeah, in the right upper corner, you have the DC potential on the top transistor M2 and the AC signal on the lower transistor. You can now swap this configuration. You can apply the input signal to the top transistor. so the AC input signal and the DC biasing signal to the bottom transistor. And if you now bias correctly, you can operate M2, the bottom transistor, in triode mode, use it as a voltage controlled resistor, and now you have a common source transistor with a programmable, or let's say a variable degeneration. So you can tweak the transconductance of this transistor depending on the bias voltage. So completely different operation, right? Also a useful arrangement. And the other thing is, yeah, you can use it for example, in RF. That's the famous dual gate MOSFET mixer. Here you have now two RF signals, or let's say two AC signals. For example, you apply VRF to the lower transistor. You apply a local oscillator to the top transistor. And what happens is that the top transistor, that is driven by the local oscillator voltage, periodically modulates the transconductance of the bottom transistor via the drain source voltage. And you apply another signal on the gate. So what you have is a multiplication operation. Yeah, if you think about the IDS formula, blah, 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 you have the overdrive voltage times VDS. If you are in triode, so you have an inherent multiplication. And if you have a multiplication, you can do mixing. So this is one of the simplest RF mixers that you could build. Maybe not the particular good one, but if the frequencies are getting high enough, yeah, this can be very useful. So again, same physical configuration, but depending on where you apply DC, where you apply AC, yeah, it's a different thing. So this gives another couple of configurations. And you should always remember the MOSFET really is a 4-terminal device. Yeah, very, very often you see just the 3 terminals, and the bulk is just not connected, not shown, because anyway it's connected to VDD or VSS. But it is a 4-terminal transistor, and you can use the 4th terminal, the bulk, also for some operation. And people do. Of course, these kind of circuits, I mean, they can be useful. They are a bit dangerous because whenever you play with the bulk, especially in bulk CMOS, you have to make sure that your bulk to drain source diode does not go forward. But if you keep this in consideration, you can use this. Even more if you are working maybe in a fully depleted SOI technology, the bulk terminal can be really useful because then you have the isolation of the thin oxide, and you cannot have a forward conducting diode. So you see quite a bit of these circuits now used in these fully depleted SOI technologies. Okay, so what can you do? So this is a bit of an unusual bulk-driven current mirror. So you can tie the gates to a high voltage, to VDD, and connect the bulks in this way, then you have a current mirror. And that is potentially lower voltage than the classical implementation, because in the classical implementation, you always have the VGS as a minimum compliance voltage on the input side. Here you have the just the diode, which can be substantially less than the VGS would be. So for low voltage applications, this can be quite useful. Again, yeah, whenever you play with the bulk, be careful. Another thing is you can also use the cross-coupled pair. I haven't shown this yet, but also one of the very useful circuits is just a differential pair with gate cross connection. Yeah, that gives you a negative resistance or a latch if you want. You can also do this in the bulk-driven version. And again, has a potential lower voltage headroom. So especially interesting for lower voltage designs. Another thing is also, again, our classical inverter. but people have also realized, yeah, that they can connect the bulks to the gates in this fashion. And if the voltage is low and you just avoid that the bulk diodes go forward, you achieve something like a dynamic threshold voltage inverter. In this way, they are using the bulk effect, which is usually unwanted because it modulates your threshold voltage, and very often you don't want to have this. But in this situation, it can be useful because it makes your eye on to eye off trade-off better. So another possible use of a two-transistor circuits and using the bulks. And the last one of this bulk theme is this configuration that we see here. Because in a MOSFET, you can also use this inherent PN junction that you have from the drain and source to the bulk. And people do use this, for example, in ESD protection structures. These diodes are used because a MOSFET, when you look just at the cross section, yeah, there are plenty of PN junctions around, and you can use them. And here's, for example, here's an example where one of these PN junctions is used. It's driven by a very, very simple current source. So the M1, the gate is a PMOS. The gate is tied to ground. So this is a very, very basic current source, not a particularly good one. But this current source is used to drive a current through a PN junction of the MOSFET. And this gives you then a CTAT voltage generator. So a voltage that has a negative temperature slope. Okay, I mean, a bit unusual, but why not? Yeah, you can use this if you want. So this example really uses the lateral PNP transistor that is also inherent in a PMOS.
Well, you just bias them in saturation?
Yes. Yep. Okay, so bulk-driven circuits, as I said, can be useful, but be careful. Some two transistors are super useful, two transistor circuits, but at least in my education, yeah, you don't usually see them. For example, when you are in industry, very early you learn that unused CMOS gates are often not allowed to be tied directly to gate, to VDD or VSS due to ESD reasons. So if you have now a logic gate, what the heck do you do with an unused input? If you look at in your standard cell library, or you have to build yourself, they are so-called very often tie 0 or tie 1 circuits, and they allow to tie an unused logic input to 0 or 1 without a direct connection. So how do they do it? They take, for example, the M1, connect the gate and the drain together. By this, you have a pull-up of this gate. And this transistor is then turned on, M2, and pulls the output to ground. And for a tie 1, you either connect now an inverter or you just flip the whole circuit around. And if you look at this, yeah, it makes really a tie 0, and there is no MOSFET gate tied directly to VDD or VSS. So that's a tie 0 cell or a tie 1 cell can be done accordingly. You need this very, very often. I don't know. I have only learned this in industry. Yeah. Another circuit that is super useful is the flipped voltage follower. I don't know if you've seen this. I mean, the standard configuration of a voltage follower is pretty simple. Yeah, the M1 would just be biased in a way as a normal current source with a fixed potential at its gate, and then M1 is the follower, so V in is transferred to V out minus the VGS of M1. So that's a classical implementation. It's the follower, not very good, but it misses potential. So whenever you see a circuit where a potential, let's say a gate is tied to a fixed DC potential, yeah, we are missing probably an opportunity because very often you can apply feedback at these nodes, and feedback is usually a circuit designer's best friend. I mean, feedback circuits are not that easy to do, but very often a feedback improves things, and this is used here as well. So instead of tying the gate of M2 to a fixed potential, for example, coming from a current mirror, to just set a constant current through M2, the gate is tied up here, and here is then a current source. And by this regulation loop, yeah, it forces the current through M1 to be constant, because essentially it senses the drain current of M1 and regulates the current M2 accordingly. So you have this local feedback loop, makes the whole construction much better. So in here is the original reference. Look it up. Yeah. So that's the so-called flipped voltage follower. Super useful. A bit similar is the next example. That's the regulated cascode. So the standard cascode we have already seen. Yeah, you put the cascode transistor on top of a common source. You tie it to a fixed potential. Done. Yeah, that's what you always learn in fundamental circuit courses. But you can as well use here feedback to make the cascode much better. Because what you want in a cascode, if you look from below into the source terminal of your cascode, you want to see a very low resistance. Because essentially the cascode should keep the source potential constant, yeah? But in the standard cascode, you see the 1/GM of your cascode transistor, which you can only make bigger if you spend more current. But you can also use a feedback loop like shown here. So this two-transistor now replaces the simple standard cascode. So here at the I-in terminal would be a common source transistor, which sends a current towards the cascode transistor M1. But now we have a second branch consisting of M2 and a bias current. In a simple case, the V bias voltage is just tied to ground, let's say. Then the gate of M2 is at VGS of M2. So that's enough headroom to squeeze in a transistor here. And what happens now is, with the transistor M2, we sense the source potential of M1 and make a feedback loop. So here's a current source. So here we have an amplifier consisting of M2 and the current source I bias. And now it works on the gate of M1. And now this loop gain of M2 and the current source now regulates the gate of M1 instead of keeping it steady. And this feedback, yeah, fights against any variation. And the net effect is that the impedance looking into M1 is reduced by the self gain of M2. If we just consider I bias to be a perfect current source. Great, yeah, just a little bit of feedback, not much extra current spent, a lot of improvement. So keep these two in mind. Yeah, if there's one takeaway from today of very useful circuits, the regulated cascode and the flipped voltage follower should definitely be in your tool chest when doing circuits. Another pretty useful arrangement is a level shift. Yeah, very often you have to do a level shift from node A to node B, and with this arrangement of M1 and M2, you can do this. You see that here you have kind of a floating battery, if you want. So you have a voltage difference between Vp and Vn of the VGS of M1 plus the VGS of M2. So you can now use this to shift a bias potential, for example, or another signal. So this level shift, or I would call it a floating battery, can also be very useful in certain situations.
Make 16 unstable, if not careful.
If you're not careful, you can probably make any feedback circuit unstable. So yes, I mean, stability is the main thing when doing feedback. And depending on how complex your loop is, yeah, this can be quite tricky. That's true. But so here, the loop is pretty simple. You have a high impedance node, so it's quite easy to put here maybe extra capacitance if the gate capacitance of M1 is not enough. In simple loops like that, it shouldn't be too big because you have probably one dominant pole and you're good. But yes, stability is always your concern, including feedback. Okay, and now we are coming to the more obscure or pretty clever section. And this leads me already towards the end of my talk. And maybe now come a few things that you haven't seen before. And I haven't seen this before. I really did look into this stuff and collected circuits. Yeah. So this is really obscure. I'm not 100% sure whether this is really useful, but it shows just the kind of things that can be done. Yeah. So what is it? If you have done very low power circuits, and with very low power, I mean creating bias currents in the pico and nanoampere regime, yeah? You will find that it's really tough to create those kind of currents because you either need huge resistors or you just start up with some medium current and just mirror down, 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 down in an almost endless chain, yeah, until you arrive at pico and nanoampere channels. And by the way, don't be afraid to work with picoampere and nanoampere. You can, yeah. In the modern CMOS processes, no trouble, yeah. So we build circuits with nanoamps of biasing all the time in our low power group. So this can be done, but it's tricky. So these people who invented this found another way to make very small currents, and what they use is the interface states. If you looked into MOSFET device physics, you know that due to the construction of the transistor, you have the silicon from the bulk, and then you have your SiO2 dielectric. So here you have a crystal mismatch, and at this interface you have a few dangling bonds, which give also rise to flicker noise, by the way. And turns out now you can fill those interface traps with charge carriers and flush these charge carriers out. And now if you use this configuration, you supply here a clock, because what you need to do is you get into the right modes in and out to constantly fill and flush those interface traps with carriers. And luckily, there are not that many interface traps, so this gives rise to a very small charge discharge current, which you can use to create picoampere currents. By the way, the original use of this arrangement was to actually have a vehicle to measure the interface traps. So this was originally a measurement circuit for process development, but you can use it as a picoampere current source. I mean, pretty clever, I think. Yeah, who would think of that? Okay.
Do you use it, sir?
I'm not sure. Yeah, maybe I'll try it out eventually.
Have you simulated it?
No.
Okay.
No. I'm not even sure if you can really simulate it. I would say I'm not sure that this effect would even be captured by the usual PSIM or PSP models. Probably not. So probably the only thing is build it, characterize it, and see what happens. Yeah. And then build your own kind of model.
So we don't really know if it's particularly stable either?
No, I don't know nothing about process variation, temperature variation. I mean, you would probably do all this characterization yourself if you want to use it. So I'm not sure if I would really recommend this. Yeah. For me, it falls into the, wow, this is clever. Yeah. I would have never thought of that. Which does not mean that very clever ideas are often the best, yeah. But for me, it's more food for thought, yeah. Just think about what you can cook up with MOSFETs, yeah. It's really interesting, fascinating. Another one, which is, this is a surprisingly useful circuit. We have tried it ourselves. And it's also interesting, yeah, this was just published a few years ago. And this works really nice. So what is it? You take two transistors, you connect M2 in diode fashion, and you take M1, which is, by the way, an N MOSFET, and you tie the gate to ground. And your first thought would be, this is completely useless, yeah? But it isn't, yeah? Because it works with leakage currents. One thing you always have to keep in mind that the MOSFET never really turns fully off, yeah? So there's always some leakage current flowing. And this group who came up with this circuit figured out that if you have two transistors with different threshold voltages, which you have in a lot of modern technologies, you can use this. So essentially you use the leakage current of M1, yeah, it's tied off, it's turned off theoretically, so only the leakage current is flowing. And this leakage current goes through M2. M2 is now working, of course, in sub-threshold operation, but you can calculate the reference voltage that comes out, yeah, and you see this is relatively stable versus temperature and process. So you can use this as a very, very simple bandgap circuit. And it's probably not as good as a bandgap, but it's surprisingly stable over conditions. And we have used this in one of our tape outs, works nicely, yeah. And the power consumption of this reference is very, very low. Of course, you're only working with leakage currents here. So what you have to make sure is how you load your VREF. Yeah, you need to load your VREF with a gate, very high ohm. And you should always take a thick oxide device, yeah, because if you have gate leakage, and even a tiny amount, yeah, since you have only leakage currents here, this can already make an error. So just load it with very, very little gate leakage. But if you do this, this works nicely. The only caveat that I would have is if you look at these formulas here, you have the sub-threshold slopes in. And turns out that the sub-threshold slope, this parameter, is not particularly well controlled in the fabs.
What's
Yes?
the range of VREF?
200 to 300 millivolts, something like that. So this, I think, has to be watched out, yeah, that the sub-threshold slope goes in, but we found out in our own testing that it's really useful, yeah, if you can live with the remaining variation. Okay, also very clever, yeah. I mean, using only the leakage currents and sub-threshold modes of these transistors. And I think this is already my last example. Let me check. No, not quite. This is a clever arrangement, and actually my co-author on this paper, Matthias Eberlein, invented this circuit. And this is really clever. And why? If you have ever built a band gap in CMOS, you know you have to use the lateral or vertical PNP transistor, the bipolar that is kind of parasitic to the MOSFET structure. If you worked with such a device, you realized that the beta is very, very poor because the whole geometry is optimized for the MOSFET, not for the parasitic BJT. So you end up with betas of this BJT on the order of single digits. Can be as bad as a beta of 2 or 3. If you're lucky, you get 10, yeah? But not like 100 or more that you would expect from an optimized BJT. Okay, so this is one part of the problem. And the second part of the problem is that if you use these BJTs, very often you find out that the collector of this PMP is your substrate. So it's tied to ground. So you cannot access the collector terminal. The only stuff that is left is the emitter of your PMP. But if you want to use this transistor in a bandgap circuit, you need to control the collector current versus VBE, or VEB in this case, yeah, if you're talking about then a PMP. So your collector is tied to ground. It's not accessible. Only the emitter is left. And now you have a beta that is very, very low. So there's a problem, right? And Now this really clever circuit from Matthias Eberlein comes in. But this arrangement, maybe it's not that obvious in the first glance, and it really isn't. Yeah, I had to sit down myself and put down the circuit equations. But if you do this, yeah, so you have here an M1. From the M1 is connected in this very strange way because we're using really the parasitic BJT. You have on the bulk the VB, here on the source the emitter voltage. So this is the VEB of this parasitic transistor, and you have a current source here, I bias 1. You have here this transistor M2, and the bias current, you pull out the I bias 2 on the bottom. And if you run through the circuit equations, you will see that the collector current, also the collector terminal, is not accessible. This is the substrate, yeah? The collector current is set to the difference of I bias 1 minus I bias 2. So by properly setting these two current sources, you have set the inaccessible collector current of this bipolar transistor, and the VEB you can also simply access. Amazing, yeah? Two transistors, pretty tricky, I would argue. Probably you need to sit down for yourself, go through the equations, work it out, look at the cross section. Yeah, it's tricky, but it works. Cool stuff. Another pretty cool one is the Bult current divider. Another interesting configuration of M1 and M2. You connect the gates of these two transistors, and in this intermediate node, you connect also a terminal where you can feed a current in or out. And when you run now through the numbers, and this is interesting, yeah, because these transistors are not in the same bias conditions. I mean, they couldn't be if they have the gate same connected. So M1 is in triode, M2 is probably in saturation, or everything in between, doesn't really matter. Klaus Bult shows this in his original paper. In any case, the current you feed in here will split exactly in half on the top and the bottom, if they are identical size. If you make them different size, you can have different scaling. Also, this is not obvious on first sight, not at all. Yeah, you have to go through the original paper of Klaus Bult and look through it, but it shows that it works, and people have used this current divider in DACs, in current steering DACs, because one way to build a digital to analog converter is take a current and halve it, 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 and so on. Yeah, so you have kind of a binary scaling and staging of currents, and then you can switch these currents depending on your digital code word, and then you get the current DAC. The big question is how you do this continuous, very precise halving of currents. And one way is the Bult current divider to do that. Yeah. Okay, so that's my last circuit examples. So I think I'm doing well on time, maybe a bit short, but maybe you have some questions. So okay, to sum up, what is the main takeaway of today? So the MOSFET is just a wonderful device. Yeah, I love it. Also, I started my circuit design career with bipolar transistors, and they are also nice. Yeah, absolutely. But the MOSFET just gives you much more capability, but it's a quirky device. Yeah, I mean, if you compare just the transconductance formula of a bipolar transistor, yeah, for a bipolar transistor, it's just the collector current divided by the thermal voltage. Done. Yeah, that's the transconductance. For a MOSFET, try hand calculation of GM in 100 nanometer or below technology. Yeah, I mean, you can use the square law, but this is just a crude approximation. So it's a very quirky device. Yeah, difficult to model in simple terms, but very, very powerful. Also GDS. Yeah, I mean, GDS is all over the place. It's hard to model, it's hard to calculate. One would think, yeah, after many decades, yeah, the transistor has been invented, that all useful two-transistor circuits have long been invented. But that's not the case, yeah. Just 1 week ago, Boris Murman from Stanford sent me one of his upcoming papers where they have, again, a two-transistor circuit found that is very useful. So, cool, yeah, I mean, why, yeah, interesting. And a lot of these two-transistor circuits are really fundamental building blocks of higher complexity circuits. If you just think about the diff pair, the current source, the transmission gate, the inverter, yeah, many circuits are just constructed from these two in many different ways. Yeah, and maybe just to make the bridge, yeah, to the boot camp. So since many complex circuits can really be broken down to some fundamental unit building blocks, which are not that different. Yeah, I think there's a lot of value, yeah, to make this semi-automatic, automatic layer generation out of these atomic units. And I'm not 100% aware what you're doing, but I think this is pretty much in line of what you're trying to accomplish here. And I think that's a very useful undertaking because, yeah, automation of analog layer generation is very useful. Absolutely, yeah, because many people today do it still by hand. So this is more than ripe for some automation. And I think by breaking down and working with these fundamental building blocks, I think this can be a very useful approach and adventure. With that, I'm the end of my talk. So thanks for being here. And yeah, if you have questions, please shoot ahead. Please.
Yeah, what's your most favorite two-transistor circuit and least favorite?
Pooh, good question. My most favorite, I don't know. I think the most surprising maybe is the inverter, really, because I mean, inverter is around forever. And then, I don't know, in 2005 or so, people just start, or let's say it was really around 2000, people started using it as an analog transconductor. I mean, yeah, cool. Huh? Least favorite, I don't know. I mean, the bulk-driven circuits are a bit special, yeah. They are not for general use. They can be interesting in some special applications, but I would not just generally recommend them. Thank you.
Yeah, Harald, I have a question regarding this like circuits that you just mentioned. I believe that also when you downscale the effect that you can have by biasing bulk on threshold is also kind of reduced. So what are the circuits that you see can span different nodes and still keep the performance, as you expect them?
I mean, one very useful circuit that you often see is, by the way, I should maybe extend a bit. In order to play with the bulk node, you need to be able to really be able to bias it to some not VDD or VSS. For standard CMOS, where the substrate is PMOS, P doping, the P MOSFETs sit in an N-well. So the P MOSFET bulk, so this N-well potential, you can always set freely. In an N MOSFET, you can only do this if you have a triple well flavor. So what people pretty often do is, for example, in a differential pair, you might want to get rid of the bulk effect. So what you can do is take this differential pair, put it in a common N-well, and bias this N-well to the common source point. By this, you pull your N-well with the common source of the diff pair. The parasitic diodes will never turn on, and the bulk effect is gone. Very useful, for example. Other things, we also used in one of our recent tape outs really a bulk forward bias is you can use the bulk effect to make your threshold voltage lower by pulling the bulk a little bit away this device from its usual position. And we had to do this on an RF divider because we were using an older technology, 180 nanometer, wanted to build a 2 gigahertz divider. The speed was pretty much on the limit. So what we did in this divider, we biased the wells a little bit forward by 200-300 millivolt. That's kind of safe. This lowered the threshold voltages, and this gave us enough speed boost in our dividers that we could hit our intended speed of operation. And this worked quite nicely. So I think there are useful tricks that you can do safely when playing with the bulk nodes. I hope that answers your question. I'm not 100% sure if I hit it correctly.
Yeah, well, actually, you added to it. So what I wanted to say is, like, you're talking about all the technology nodes, but when you kind of go to lower technology nodes, it's a question, how much actually you can, by biasing bulk, affect the threshold voltage and play with it. That was basically, so based on that, you definitely, there are less circuits that you can play with. I was, going into that direction maybe.
Okay. If you're speaking really about nanometer node technologies, yes. I think you have to distinguish two ways. In FinFET technologies, the bulk effect is very, very low, almost non-existent. So in FinFET technologies, you cannot use the bulk effect. On the other hand, you don't suffer from it. So that's one thing. In FinFET, you really don't have this option. In PD, so in FD SOI, so fully depleted SOI, where the buried oxide is very thin, you have a pretty decent control from the backside on your transistor. And what you see in the publications is that people really use this a lot. Especially in 28 nanometer SOI or 22 nanometer SOI, people really, again, use the bulk node a lot to adapt the threshold voltage according to operation. You can use it for trimming in an analog circuit, for example, because it's an independent terminal that you can nicely use for this, or you can use it in a digital circuit to modulate your threshold voltage, to alleviate your I-on versus I-off trade-off, because you can bias it in a way to have a low threshold voltage when the digital circuit is active and should have high speed, and you can bias in a different way during off mode when you want to have very little leakage current. So you see, especially in things like 22 SOI, people use actually the bulk nodes a lot.
What about bulk CMOS? I was, you mentioned these two special technologies, one that actually use the advantage of the flipped well and thus, change of the threshold through the bulk, and the other that does not have. My question was more going into the direction of bulk CMOS, lower technology nodes.
Lower technology. I think my feeling is it got a little bit less popular because usually in these technologies you have a couple of VT flavors in your transistors. So you can select the right transistor with the right threshold voltage, because usually you have maybe an LVT, a standard VT, a high VT transistor, maybe more. So you can just put the transistor with the right threshold voltage in. You still have the bulk effect. It's there. So it might still be useful to compensate it. Why not? Yeah. And if you want to dynamically adapt during runtime your threshold voltage, also playing with the bulk can be useful. So I would say, why not? But a few of the uses has been gone away due to just the availability of a couple of threshold voltages in your transistors.
Mm-hmm. Okay, thank you, Harald.
Sure.
Don't you feel you're basically and you're basically exploiting the fact that manufacturers try to fight against, like specifically this trap?
Yes.
I mean, they would like to reduce it in order to reduce the noise.
true.
Try to exploit it. So,
Yeah, that's true. But you know, I mean, analog circuit design is a bit like hacking. Yeah, I mean, you are given what you have in a technology, because if you just think about it, yeah, doing analog circuit design in CMOS is already a hack to begin with, because your transistors are just simply optimized for digital switching, nothing else. So I would say, welcome. Yeah, I mean, I always found it an interesting challenge as an analog circuit designer. Yeah, to just take what you got and make the best out of it. If you think along this direction, yeah, what is an on-chip inductor? It's hacking your metal. Yeah, because usually you don't want any inductivity on your interconnects. In an inductor, yeah, you just make the wire artificially longer and bring it into mutual coupling that you have. I mean, is that a hack? Exactly, or the metal finger capacitors. I mean, that's a pure hack, if you think about it, right? So I would see in this way, a hack is a good thing for me, yeah? Because if you figure out to use something what you got really creatively, why not? Of course, yeah, you have to be very careful that whatever you want to exploit is not something that the foundry tries desperately to get rid of, yeah? But if this is an effect that is stable enough, for example, the intermetal capacitance is pretty stable, use it, yeah? Why not?
But they have some interest in keeping that stable in order to get your timing.
Exactly, and then you have a mutual interest.
Yeah, in that case, but you
Yeah.
mentioned that it's low.
The saturation stop is a different thing. Yeah, it's not that well controlled. It's often not that well modeled.
Maybe they kind of monitor the threshold voltage and what they change things.
But on the other hand, even unmonitored things can be surprisingly stable. So my former student, Matthias Eberlein, who invented this one circuit, also used the parasitic N-well substrate diode in a bandgap circuit, because he came up with a few new architectures for temperature sensors and bandgaps. And usually the forward mode of this N-well P substrate is not controlled at all. Yeah, I mean, under normal operation, this is always reverse biased. If you are lucky, you get a good capacitance model for that. But he used it really in forward bias, and it turned out that he did, and his company that did characterization on that, and they found out actually that this uncontrolled, pretty much unwanted junction, yeah, is really stable because it's a buried junction that is good. Yeah, this was in a FinFET technology because the FinFET transistor was not really good for that use. It's buried junction. It's very stable. It had a very ideal diode behavior over many decades. Why not? Yeah. But be careful. Yeah, I mean. Whenever you deviate from the standard operation, from the standard components that the PDK offers, you might be on your own. So be careful. You need really to know what you're doing. That's definitely true. Yeah, you need to know what you're doing. You could, if you really exploit, then otherwise, let's say, unmonitored parasitic effect. I mean, you could always try to do a small test structure in your design, so then in mass production, you yourself can at least monitor it. Why not? Yeah. I mean, I have seen quite a bit of designs where people did this, maybe not for unwanted, but also to monitor something like RC variations. Yeah, if you have a kind of an analog filter made out of some resistor and capacitor, you might want to monitor the RC product during production. Yeah, so you can put the small RC reference somewhere, so then measure the time constant in production can be quite helpful. I mean, you would get kind of similar information from the PCM data, but the PCM data you get by wafer, maybe a little bit of wafer distribution, maybe you just get the average of a lot, I don't know. If you have it on your chip, it might just be a very small area overhead, and you can measure it directly on each chip. Might be super useful. So yes, I have seen quite a bit of instances where this has been done. Yes, please.
As you said, that buried junction is generally it is quite stable, particularly in FinFET.
Yeah. It's a good device.
Right? Yeah.
Yeah.
But I have read somewhere that you can put directly metal on the substrate so that you can get a Schottky diode, so that your band gap will operate at a very lower voltage.
You can do this in some PDKs. This Schottky diode is already there as an element.
Oh, okay.
So depending on your PDK, you can again hack it, as you said. You can always try to. Maybe another good example of hacking. A few years ago, when people started to build CMOS oscillators, they found out that they had no good varactors. Because in the bipolar technology, you often have a kind of optimized PN junction that you can use as a varactor. In CMOS, you don't. And then people found out that a MOSFET in accumulation mode is a pretty good varactor. So how do you do that? You put an N MOSFET in an N well. I mean, that's pretty much hacking, but this is now the standard. Yeah, if you now look into the PDKs and the CMOS oscillators, yeah, pretty much everyone uses an NFET in N well as an accumulation mode varactor. This was also not the original intention. So yeah, why not? All right. I think that's about it in terms of questions. So I hope you found this entertaining and useful, maybe inspiring. Yes. So if you are going to be or are already an analog circuit designer, congratulations. You have chosen a very interesting field, a very rewarding field. So yeah, just keep going, and you see there are plenty of things to be innovated out there. Oh, maybe one last, yeah.
But more like we have students from the Philippines who are right now.
Okay.
Who also would like to be good analog designers.
Yeah.
What would you advise them?
Just do it. I know of no good circuit designer who was born a good circuit designer. It's just practice, practice, practice. And just expect that you're never done. Yeah, I do now circuit design for more than 20 years. I'm still learning. You're never done. It's just, practice. Read good books. There are very good books out there. Try to understand the devices that you're working with. Get into the device physics, even it's a bit hard. Try to get really good understanding, a solid understanding of the transistors, of the passive devices that you're working with. Read good papers, read good books, and just do it. Yeah, the more circuits you build yourself, the better you get. Yeah, just expect it takes a few years. Yeah, and a good mentor helps. So a lot of circuit designers learn to get better by having a good mentor. Yeah, a more experienced circuit designer that just gave them a bit of a head start of do this and don't do this. Yeah. In the beginning, you don't understand, but sooner or later the picture forms, and then you get it. Yeah, why this was a good decision, why this is a bad decision. Yeah. So, but that's it. Yeah. I think there's no better way.
Harald, I have one question that maybe digs into this. So if, the good mentor is not available, the books are our next good thing. So can you recommend, I mean, we know a couple, but I would like to hear from you. What do you recommend to your students, though they have a good mentor, but still?
I can give you my top 3 analog circuit design books. Yeah, my all-time classics. One is the Gray and Meyer book. I don't know the exact title. I think Analog and Design, also Analysis and Design of something like that. Yeah, Gray and Meyer. Google it, you find it. It's very famous. I like it. Yeah. This is one. Then of course, all the books from Behzad Razavi. The analog, there's also an analog microelectronics book from him. I recommend that. There's also a very basic microelectronics book. Probably you can jump over that quickly, but there's an analog circuit design book from Mr. Razavi. This is also very good. And then there is the Analog Design Essentials from Willy Sanson. It's a bit unusual book because it consists of more or less the slides of his lectures and a bit text. But I also like it because if you go through it, yeah, it has a big amount of interesting tidbits. So if you ask me for my top 3 books, that they are, yeah, Gray and Meyer, Willy Sanson, and Behzad Razavi.
Excellent. Thank you so much, Harald.
And by the way, maybe a small hint, if you're not yet an IEEE member, and by the way, I'm not paid for this. Yeah, just out of yeah, I think that's really useful. Yeah, become an IEEE member, join the Solid State Circuit Society. They have tons of good training videos online. Get yourself a subscription of the Bible, yeah, which is the journal of Solid State Circuits, the JSSC, the red cover. Yeah, get it, read it. That's really your way to success.
Okay, excellent.
Thank
you so much, Harald.